we've been discussing, applications of artificial intelligence with telemedicine for early diagnosis screening of age-related macular degeneration, diabetic retinopathy, and glaucoma, for all three diseases, which are all potentially blinding. And this is me who's up there on the screen. You kindly introduced me, so everybody's heard all that. Let's see here. Okay. Let's advance. Let's go somewhere. Oh, I see. Maybe here. Try that. Yes. Okay. And so we're doing an imaging program combined with artificial intelligence on a telemedicine platform, and we're using it for disease screening and collaboration. I'm doing this in collaboration with my good friend Alaudin Buyan, who's the head of iHealth Screen, a private company. He's done all the heavy lifting in developing these very complicated deep learning algorithms. And I kind of go along for the ride in my imaging lab at New York Eye and Ear. So we take lots of pictures of the patients, and we use our clinical expertise to vet the artificial intelligence. So as we develop the programs, we have to be sure that we're getting mostly the right answers, and that still has to depend on human grading at this point before we turn it loose on the public. Like I say, AMD, DR, glaucoma. Alaudin just received a very nice grant from the NIH, Small Business Initiative, the iHealth Screen, to fund the study that we're doing now, which is going to run for 3 years for both screening and prediction. So just to go on a little bit, I'm going to give you the conclusions of my talk right now so that I don't run out of time, and I'll just say them very briefly. But we have concluded, what we will show you, that neural networks, deep learning, can detect and classify diabetic retinopathy and age-related macular degeneration, and to detect what at least are glaucoma suspects from fundus photos alone. And that's important to recognize because, you know, there's a lot of people out there who are talking about detection and this and that, and they say, well, what do you need? Well, you need an OCT, you need an fluorescence, you need fundus. So wait. You need genetics, and hold on. You know, that's a lot of hardware and that's expensive. You want to be able to do this with just a fundus photo. And from that fundus photo, machine learning can also predict, this is a part that's amazing, still amazing to me. You can predict which patients are going to progress over 1 to 2 years. And for this, you need the photos, and you also need a lot of clinical data about the patient. But the prediction is uncanny. And then what we're putting together are cloud-based telemedicine platforms and fundus cameras, which we're going to try to make available for community screening and referral. Okay, so I thought it might be interesting to people to hear a little bit about the fact that we've published all this, so it's not just a whistling Dixie, as you might say. So Alaudin has put this a lot of hard work, and over the last 5 years, culminating into these 2 very seminal papers, which just came out this year, showing how much work it takes. One on predicting and stratifying AMD, and another one on classifying diabetic retinopathy in an automated way. So it's all peer-reviewed and out there. People who are not familiar with some of the nomenclature, I'm not going to go into any detail, but you hear the words machine learning, and you hear deep learning, and then you hear neural networks, and they all sound like foreign language, but I'm going to give you just a little tour of what those mean. So machine learning, the way to think about that is that it's often used for prediction of outcome, and the data that is used to train the algorithm usually is fairly copious. You start with many patients, you start with many known clinical features, so you know a lot about these patients, and you also know the outcomes. So you have to give the machine something to work on, and the outcomes you want to have just a few specified ones. The patient lives or dies, strokes or doesn't, goes to advanced AMD or does not. So now the machine model works on all those parameters and the outcomes, and it finds the best combination of the clinical features and the imaging features to predict the outcome. Once its model is working and running well on the training data, then you have to go out into the real world or to test data to see that it actually does perform as predicted. And you might want to think of this I think of it this way. It's really kind of like multivariable regression. You throw in a whole lot of variables to see which ones are the most important, but it's done in a very, very complex and deeply statistically driven way. So, and what I'm going to present in a few minutes will be using machine learning to use retinal image data and demographics to predict advanced AMD. Okay, so deep learning is quite different. Deep learning is pattern recognition learned from what people call big data. So really, it will only work when you can give it hundreds of thousands of photos to train it, if you're training from photographs. So it's very powerful. The reason it hasn't been done until just the last few years is the computers couldn't handle it. And the algorithms would run, for days. Now we got the power, so you can give the machine 100,000 digital photos. You can tell it only one thing, basically it's AMD or it's not, and say, go to work. And then this thing goes through an incredibly complicated procedure of convolving different layers of information with others at different scales, small scale, large scale, color scale, edge detection, tries everything that it can possibly do, but we're not helping it. It's just doing it by itself to try to learn, like we would almost learn like a child to recognize. Okay, so neural networks, they learn from experience. And so you give them lots of data, you let them process the data, just like our neurons do, and then it comes to an output, and then it looks and says, oh, did I get it right or did I get it wrong? Oh, did pretty well. I'll go back here and I'll increase this one, I'll decrease this one. And like the neurons in our brain, as we learn, the neurons that are firing and producing the right outcome get strengthened, and the ones that are missing and putting you in the wrong direction, they kind of get suppressed and they kind of get put aside. And that's kind of the way this works. And as far as decision making, here's an example of a neural network which is given two pictures and is processing it. And this is a network actually, which has been trained and now it's pretty good at distinguishing. So every time it looks at that picture of the dog, it processes and comes out with dog. But it had to give it a lot of pictures of cats and dogs before it can do that. Okay. So here we have it, a telemedicine deep learning platform for AMD, diabetic retinopathy, and glaucoma. And a picture of a little girl who's been reduced to edges by the software. Again, mentioning Aladdin's nice grant there. So here's what we've done. The way to think about it, what are the basic components? So if we look at it from a high level, first you need to have inexpensive, good quality, and user-friendly photography. So out in the field, it can't require, a trained retinal photographer. Those guys are very expensive. The camera can't cost $50,000. That's not going to fly. But it has to be decent quality, hopefully non-mydriatic. If you can get those pictures, then you can forward them up on compliant data pipelines, which follow the regulations, and get them to our deep learning algorithms. And the algorithms at the present level have to be tuned to the disease. So you have to have one that knows how to look for DR, one that knows how to look for AMD, and one that knows how to look for glaucoma. Eventually, it'll all go into one gigantic pipeline, like a human who would be able to just look and say, I know what this is, but you got to have all tuned. So here's the way I like to think of it, the way we're doing our field testing. So cloud-based data management. So you take a picture of the patient over here, and then you put his image up here. And then somebody tries to stop you here saying that's illegal. Then you say, no, 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 I have permission. You go ahead and put his image up here. Then you bring it down here to the server. The server works on it. And you go here. And now you think, the machine thinks. Now this has to be a very smart machine. It has to have a lot of neurons, a lot of levels, a lot of computing capacity. And so that's the next thing that happens. And I just put this picture up there because I happen to have one. I happen to be very fond of this fellow. Maybe you don't like him, but anyway, I like him. One of my favorites, Felix Mendelssohn. Okay, looked at 4,600 age-related eye disease study subjects. That's a big study here in the States. It's the premier study for AMD. Collected 116,000 color photos that had been graded for none, early, intermediate, or advanced AMD. So we had those gradings by experts. Then the network was trained to classify, and we really went for the most important classification. Is this patient or is this image referable AMD, or is it non-referable? If the patient has referable, that would be intermediate or advanced, that patient should go to an ophthalmologist and then continue to be followed with them because they're already either at high risk or have already progressed. If they have early or no AMD, they can come back in a year and probably nothing's going to happen. And that's how we're going to unclog the system, hopefully, from the primary clinics to get them to the eye doctor. And our neural network achieved 99% accuracy on separating from referral level to not. So, and again, this is on the AREDS data. Keep in mind, there are two theaters of operation here. There's the digital cyber theater, where you bring in tons of beautiful data from a known study where the images were all sitting there and being taken by expert photographers, and you train your computer to work on them. And then there's the real world, and you go out in the trenches. And in the trenches, you have real patients who, maybe they cooperate, maybe they don't dilate, or maybe they do. Your camera maybe works, maybe it doesn't. I mean, again, we're talking reality. And when you're out in reality, you got to set your bar a little lower, but you can still do extremely well if you have the right equipment and are persistent. So for diabetic screening, this was a field test. So I'm not going to discuss the original in vitro work, but we actually took 974 diabetic patients who had been imaged prospectively in the New York Eye and Ear clinics, rated by retina specialists. And then we had trained neural networks, already trained to classify. Now for diabetes, referable means they have either moderate, severe, or proliferative disease. And non-referable would be none or early, depending on low to microaneurysms, exudates, and so forth. And the neural net on real world data, in this case, achieved a sensitivity of 82%, which is good enough for FDA approval, which is the gold standard, and specificity of close to 94% for referable diabetic retinopathy. So we're doing quite well in that department. And finally, for glaucoma suspect screening, here we're aiming at something fairly simple, but it's probably good enough to catch most people. So we looked at 1,500 color photos that included the disc, and we pulled these photos from the ARED study that I just mentioned, Singapore Malay Eye Study, and this optic nerve evaluation data set specifically for glaucoma. First, experts went in. You always have to have the ground truth. Experts measured the vertical cup disc ratio on every image. Then we go in and we train the neural net to classify, but we really want to keep it relatively straightforward. Two outcomes. Glaucoma suspect is somebody whose CDR is greater than 0.5. A non-suspect will be somebody who's less than or equal to 0.5. If we can just hit that benchmark, we'll save a lot of sight. We can get those people with those larger cup discs. And our sensitivity, again, turned out to be 83%, specificity 94% for identifying glaucoma suspects compared to the expert grading. So if every one of those suspects could get to an ophthalmologist or an optometrist or somebody for longer term follow-up, again, glaucoma is a silent disease. People don't know they have it. The pressure doesn't hurt until it gets to 45. They don't realize their vision's bad until it's tunnel. But this could save a lot. This could save a lot of vision. So we hope to deploy all three of these in the field. So, and then last but not least, which I promised to tell you, is that we do have a prediction model. Now we looked at the ARED subjects, and we looked specifically at the ones that had 1 and 2 year follow-up, because we wanted to look in that window. And we found 923 who progressed to advanced in 2 years, 901 who progressed to advanced in 1 year, and a much larger number, 2840, that did not progress over that period. Then we let our deep learning model make very precise severity level determinations on their fundus photographs. So now we're really digging in much more than referable, non-referable. The 9-step scale is a pretty fine scale, and that took some training and some work. But the deep learning can come up with that scale. Once you have that data, you still need more information. So now we're into machine learning. Now remember, machine learning wants to have a lot of information. And so the machine learning, we gave it the initial severity scale, socio-demographic data, age, race, et cetera, and other traditional AMD risk factors, which we know are in there, smoking, hypertension, et cetera. Gave it all those parameters and let it run and let it develop a prediction model now for who's going to convert in 1 or 2 years. And again, I'm still amazed, 88% accuracy on prediction of 1 and 2 year conversions. So you can look at a person who's sitting there with dry AMD, not advanced, and run this test and find out that this guy has a significant chance of converting to advanced. It could be wet or dry within a year. That's kind of uncanny. And so that could be a big help in patient management and patient compliance. So that's where we are. That's where we hope to be in the future. I hope I've made it clear that these deep networks can classify AMD from fundus photos alone, also diabetic retinopathy. We can predict progression in AMD only right now. We have cloud-based telemedicine platforms, and that's quite a bit of work to put together. The fundus cameras are out there. They're much less expensive than they used to be. They get good images. In the future, we'll be able to hopefully screen for all 3 of these diseases in the community and even provide some prediction so that they can advise and individualize patient management. And so with that, I will conclude. Thank you. And here's me and my fellows, and there's the guy that did all the work, and thanks for your attention.